The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Today's lecture is on intermolecular interactions. And it's really one of these favorite topics where, I can say, well, this is the origin of life. How do gases actually condense? And we can build a really, really simple theory for how gases condense based on what we know, based on second-order perturbation theory, based on some hand-waving stuff. And it really is something from nothing. But it's also an example of what we do in physical chemistry, where we explain one phenomenon by taking something that seems to be unrelated and building a model around it and explaining this surprising thing. And that's what's going to happen today. We'll talk more about that. Okay, now, last time we talked about wave packet dynamics. And so with wave packet dynamics, there's first the pluck. How do you start the system in some superposition of eigenstates? And then there's the evolution of the pluck, which is usually some kind of particle-like state that follows Newton's laws. The center of the wave packet follows the Newton's laws for the position and the momentum. But if you make a wave packet in a real molecule, the molecule is going to be not a harmonic oscillator. There will be anharmonic effects, which causes the wave packet to dephase, but the center of the wave packet continues to move as if it were in a simple potential. And it can dephase and rephase and all sorts of complicated stuff, and that can be very interesting. Now, when you take the step from a diatomic molecule to a polyatomic molecule, you have 3n-6 oscillators cohabiting in the same house, and they're going to interact. And so if you start a wave packet on one Franck-Condon bright mode, because of anharmonic interactions handled by perturbation theory between modes, you start to get this wave packet leaking out into other modes. And so the expectation value is going to exhibit oscillating time dependence associated with the bright mode and some of the dark modes that are anharmonically coupled to the bright mode. And it can get pretty complicated. But you can understand all of it because you have perturbation theory. And so you can say, okay, this time the wave packet, some amplitude of the initial wave packet is transferred to a different mode. And when does that happen? Stationary phase. It happens in a particular geometry. And so you can be asking, okay, when is this excitation transferring? How strongly? This is a very, very complete picture, and it's very much like classical mechanics because it's localized. Then we talked about Landau-Zener. And the Landau-Zener is basically a simple idea that you also understand from real life. And it has to do with how does a wave packet jump from one potential surface to another. And again, it's stationary phase. At the internuclear distance of the curve crossing, the wave packet has to decide which curve it's going to follow. And it depends on the velocity of the packet at the curve crossing and the difference in slopes of the two paths that it has to choose between. And all of this is very simple. Now, I am trying to create an exam problem which is related to Landau-Zener. And this is hard but if I succeed, then you can expect to see it. The last thing I talked about last lecture was the Zewail pump probe experiments. And this is a beautifully graphical picture of how do you create something and then probe what's happening. And again, I hope that I can come up with something pictorial for the exam on the Zewail problem. Okay, now before I talk about intermolecular interactions, I want to do a little bit of tying up loose ends. You know about non-degenerate perturbation theory. Now there's another kind of perturbation theory called degenerate perturbation theory. And this is when non-degenerate perturbation theory fails because H Ij over E I 0 minus E J 0 is greater than 1. Well, then you've got a problem. You can't use ordinary perturbation theory. You have to diagonalize. You diagonalize a 2 by 2, or you diagonalize all of the little cases where this is violated. That's called degenerate perturbation theory. And there's a little bit of an extra recipe for how do you put information about remote states into the part of the Hamiltonian you diagonalize. That's called the Van Vleck transformation, and I'm not going to talk about it. But basically, you fix things up by diagonalizing a 2 by 2 or a 3 by 3, and then do ordinary perturbation theory. And then there's variational. The variational model is something we've used mostly in a minimum basis set for talking about diatomic molecules. And in the variational model, we minimize energies by optimizing mixing coefficients. Now, perturbation theory is implicitly an infinite basis. Usually the infinity doesn't matter because the interesting stuff comes in from relatively low-lying levels, and the infinite number of very far away levels just modifies the energy levels a little bit, and you don't have to worry about it. The variational method, you choose your own basis set. Now, the choice of basis set is frequently dictated by convenience, and the basis set is often not very large or not orthonormal. And so there are problems with how do we deal with basis functions which are not orthonormal, especially not orthogonal to each other. And there's a transformation that you can do to make that work out. I mean, the problem is basically where the secular equation is this for the variational method, and this is the overlap matrix. And when the overlap matrix is not the unit matrix, we have what's called the generalized variational calculation. And there are methods for handling that. And I have often introduced those methods on a final exam. Those are just statements. Okay. So variational is not guaranteed to give the exact answer. And it can't if you don't use an infinite basis. Perturbation theory implicitly uses an infinite basis. And you should feel confident that you're getting close to the right answer. And you can know what sort of errors you're making. Okay. Yes?
So when you go to very high orders in perturbation theory, your convergence is not necessarily better.
That's correct.
On the real solution. So
okay, but that's...
You know when to cool it.
This is... The problem there is that you cannot include correlation in perturbation theory. And so there are things that are outside network of things that I've described. And so correlation effects, where the particles can move in some way that they know about each other, that's very difficult to build in via perturbation theory. But when we don't have correlation, then perturbation theory makes an error, and you know how big that error is. Okay, and then we know that we can diagonalize a matrix by some kind of unitary transformation. And the columns of T dagger are the eigenvectors, and the rows of T are the inverse. Rows of T dagger, or the columns of T, are the inverse. And so if you want to make a wave packet where you have some initial state, T equals 0, you want to express that as a linear combination of eigenstates. And this sort of transformation provides that information if you know how to use it. And you can get approximations to all of these elements of T dagger from non-degenerate perturbation theory. And on the second exam, that was one of the things you didn't do very well on. And so you can see that again. All right. Okay, so now we're going to talk about intermolecular interactions. And up until now, we've been talking about isolated molecules. And you have a lot of insights about how isolated molecules work, or at least what kind of stuff you need to be able to make predictions about isolated molecules. And perturbation theory is a very important tool in building that insight. In almost every problem, which is not an exactly soluble problem, perturbation theory gives you at least a hand-waving argument for what's going on. Everything we did with LCAO-MO is really based on perturbation theory, or at least the interpretations, especially when you go from homonuclear to heteronuclear. And when we talk about what the various orbitals look like and why they look that way, okay. So perturbation theory can also be used to talk about, we have two particles, A and B. And we have the origin of coordinates, and so this is the coordinate for A, and this is the coordinate for B. And this is the interatomic coordinate. And so we're interested in what happens as a function of this interatomic distance. And can we use perturbation theory to be able to say something about that? And the answer is you betcha. Because basically we understand how these two molecules work. And so we have to somehow build in some insight into what is the interaction between these, and then use perturbation theory to quantify it. Okay, now this is a situation where we're going to say atoms A and B are filled shell, or whatever you want to call it. They don't need to make another bond. They're not going to bond to each other. There's no covalent bond between A and B. There's no charge on A and B. There's no donor-acceptor. All of the things that we can understand by looking at individual systems, they're all turned off. These molecules do have energy levels. And so if we could find some way to talk about the weak interaction between them, well, then we have the basis for perturbation theory, because we have weak and we have energy levels that we know for the two molecules. And so if we're going to do perturbation theory, it'll be second-order perturbation theory, because we are going to be interested in how interaction of A with B causes excited states of B to mix into B, and vice versa. And so one of the things you know about perturbation theory, if you're talking about the ground state of a system and you do perturbation theory, what happens? What happens to the energy levels? I mean, you have, for second order perturbation theory, I'm sorry?
Everything gets, things can increase or decrease, actually. The H term gets squared.
Yes.
Some sign information. But depending on whether a level that's lower.
But if we're talking about the ground state.
If it's the ground state, then it has to go down.
Right. And so that's the key. We know that if we're going to do second order perturbation theory, and we're going to be asking questions about molecules in their ground state, they're going to be stabilized by interaction with other molecules. It doesn't matter. As long as there's no bonding interactions or very strong short-range interactions, this sort of a problem is guaranteed to give stabilization of the ground state of the system. And that's really a surprise because, yes?
You're treating the system as though it has like a ladder of energies and everything is already at its lowest? Yes.
Well, okay, and you know, I'm not allowed to talk about statistical mechanics. I can actually, because we do it. We now do some statistical mechanics in 560. So you know a little bit, and you know that that molecules like to be in the lowest energy levels, and so we have these ground state molecules in a gas, and we understand their isolated properties, or we could understand. And then what happens here? Somehow there's interactions between them. And now, first order perturbation theory, you're allowed to have a sign. But you're allowed to have a sign for diagonal elements of the perturbation operator. And okay, so we'll just continue with this. So we want to talk about a Hamiltonian for the system, which is the Hamiltonian for particle A, the Hamiltonian for particle B, plus some interaction term between A and B. Okay. Now, the typical interaction between two particles is a dipole-dipole interaction. If molecules have dipole moments, then we already know something about what they want to do with each other. And from electricity and magnetism, we know, this isn't quantum mechanics, we know that we can write a general formula for the dipole-dipole interaction. So that's the general formula for the dipole-dipole interaction. And it's a little more complicated than you would like because there's two terms, and this one is kind of a puzzling term because you're projecting a dipole on the interatomic axis. And so we'd like to be able to simplify this, and we can simplify it by simply drawing some vectors corresponding to the dipole moments. And so we have the dipoles oriented like that, or we have the dipoles oriented like this, or like this, and like that. Now this is a reduction. You know, these are the simplified terms where these guys are irrelevant, or at least you don't have to worry about the projections. And we know that this is an attractive interaction. This is an attractive interaction. This is repulsive. and this is repulsive. And we know also by plugging into the formulas, we know that the energy for this one is minus mu A mu B over 2 pi epsilon 0 r cubed. And this is minus the same stuff except a 4 in the denominator. So that means it's less attractive than this one. Minus means attractive. And then we have two terms that resemble these except they're repulsive. So there's 4 terms. So there's 2 terms that are attractive and 2 terms that are repulsive. And they come in pairs, one positive, one negative. And so you might naively say, well, you can't win. If the particles are randomly distributed and randomly oriented, there will be no stabilization, even with dipoles. But that's not true because the molecules try to find an orientation which is more stable than the sum of the energies without the dipoles. And so maybe we could draw a picture and try to figure out, well, how that would be. So does anybody want to give me guidance to a picture showing, let's say, 4 dipoles oriented in the corner of a square? And what would be the stable arrangement for 4 dipoles oriented on the corners of a square? Okay. Right? So we have 2 attractive interactions, 2 more attractive interactions, and then there are repulsive interactions this way. But we have nearest neighbors, and they're stronger than the repulsive interactions. And so for one layer, that can win. Now, we have another layer of 4 dipoles. And if that layer is so we have this another layer, and there'd be 4 of them. And what would happen? What would be the stable arrangement if I have a dipole above this one? Is it going to be this way? Right. And so the next layer, all the dipoles are reversed. And so you can conceive of an arrangement where the dipoles would adopt a more stable arrangement. And statistical mechanics, or whatever you want to call it, guides that. And so we can say, all right, the ensemble of dipoles interacting with each other can arrange to be energetically stabilizing. And so we can reduce the problem to just one picture, say this dipole or that dipole-dipole arrangement, and do second-order perturbation theory. And that will be an overestimate of the stabilization, but it will be proportional to the stabilization. And so we can get what we need for a very complicated infinite number of particle problem. Okay, and another thing that I want to ask you, suppose you have 2 particles and they come together, and so they come together with some kinetic energy, and they can't get rid of that kinetic energy, so they come apart. Now, if you have 3 particles, if something drives them together by mutual attraction, then one particle can take away the excess energy. You can end up leaving the 2 particles bound together. That's how you make liquids. So the driving force for the attraction between atoms or molecules is somehow related to what we're going to derive here. And that is the only way you make liquids from gases. And it's really strange because we're going to be talking about energy levels and interactions between molecules and somehow coming up with a picture that leads to universal attraction between molecules that are not charged, not reactive, not anything, and they will always attract each other. And that's the first step towards making liquids. Okay, now the important thing in all of this is that the interactions are small compared to the energy levels of the individual molecules. And so that's why we're doing perturbation theory. Okay, so in perturbation theory, we have an H0, and the H0 is, I got to make sure I use consistent notation. Well, I see I have inconsistent notation in my notes, but anyway, okay. So we have the Hamiltonian is the individual system Hamiltonians, the sum of the two, and the first order term is VAB. And so whenever we can separate a system, we know that the zero order wave functions are products of the eigenfunctions of HA and HB. And the energy levels, the zero order energy levels, are the sum of the energy levels from HA and HB. So we know that we can write H0 psi A alpha psi B alpha. Oh, so this guy, HA operates on psi A, and it treats this as a constant. HB operates on psi B and treats this as a constant. And when you do that, what you discover is that we get okay, so these are our energy levels, and these are our basis functions, and we are off to the races. So this is E0, and this is psi 0 for the system. Okay. Now, the first thing we do in perturbation theory is we say, let's look for the first order correction to the energy. That's the diagonal matrix element of the H1 term, this. So suppose we do have dipole moments on both particle A and particle B. So that's the first order energy. Well, this is just the dipole-dipole interaction. And so we can take the reduced formula. We're just going to regard VAB as mu A dot mu B over R cubed. And so the energy is minus 1 over 2 pi epsilon 0 r cubed. I left out the 2 pi epsilon 0 on this formula, but and so skipping a couple of steps, we have mu A, mu B, the expectation value of these. So if there's a dipole-dipole interaction, there will be a first order correction term. And keep in mind that these guys can have signs. And that sign does appear in the first order correction to the energy. But that's basically these pictures we drew here. We have a dipole pointing this way and a dipole pointing that way. That's repulsive. And that's all. So there's no surprises here. Okay, but the important thing is that the energy, if we have two molecules with dipoles, we get an interaction energy that we can calculate. But the interesting thing is going to be when we have molecules where at least one of the molecules doesn't have a dipole. Then we're getting into territory that we didn't think we understood. So, but we're continuing with the problem where we do have dipoles. Well, I just want to make sure that yeah, okay, so for the second order correction to the lowest energy level, we have the sum over m, which is two quantum numbers, and m is not equal to the 0, 0 state. Alpha is not 0, beta is not 0. Sum over everything except the ground state. And what we have is an integral of psi m 0 star VAB psi 0, 0 d tau squared over then E 0, 0 minus E 0 m. Standard formula for second order perturbation theory. This is the ground state. This is some excited state. This is negative. This is squared. And this is squared. So this overall correction is negative. Now we can unpack all this, and we can write the various terms in more instructive form. And what we'll have in the denominator will be E0, well, EA0 minus EA alpha, and plus EB0, E0B minus EB beta. And we can rearrange that. So we have E0A plus E0B minus E A alpha plus E B beta. So we have the ground state energy and the known excited state energies, and there's the difference between these. So that part is simple. And the matrix element also simplifies to the product of the dipole moments squared. Okay. Now, suppose I just want to make sure that I'm doing this in the order that appears in the notes. Suppose mu A is not 0 and mu B is equal to 0. Okay, well then all these formulas go out the window. Because nominally we think, well, this B doesn't have a dipole moment. But suppose we have a particle B in an electric field. The electric field will polarize B. And if we have molecule A, which has a dipole moment near B, it will also polarize B. And second order perturbation theory tells us how to handle that. And so we get a formula, a second order correction to the energy of B, and we call this B, induction. And that's going to be mu A squared over 4 pi squared epsilon 0 squared r to the 6th times some beta not equal to 0 of this squared matrix element integral psi b star beta mu b psi b 0 d tau b squared over e b 0 minus e b beta. Now, I just told you that the dipole moment for the permanent dipole moment for particle B is 0. But this is not the permanent the expectation value of the dipole moment. This is an off-diagonal matrix element of the dipole moment. This is the transition dipole, transition between V equals 0, well, between the ground state of B and some excited state, the beta excited state of B. Well, we can write something like that. Because we know for all molecules, there are transitions which are electric dipole allowed. Now, they could be between electronically, the ground state and an electronically excited state, or the ground state and a vibrationally excited state. So we know something about these. We know the rules for when they're not 0. And this is a perfectly reasonable thing because it says this is related to the transition of the intensity of an observable transition. And this should really start to make you a little bit appreciative of perturbation theory, because we're taking something which you can observe, a transition strength, and using it to describe an interaction between two molecules. So it's a relationship between two apparently unrelated phenomena. Physical chemistry is full of that. You build a model, and the model is telling you that certain things are related. And how are they related? Well, they're related by 1 over r to the 6th. They're related by the strength of the dipole on one, the permanent dipole on one, and some transition intensity derived quantity on the other. Isn't that neat? And since the dipole, we say, well, this is a dipole interaction, and it's the mu A, the dipole on A, is inducing a dipole on B. It's not inducing anything. It's using transition dipoles, but it's creating something that looks like a permanent dipole, and you have a dipole-dipole interaction. But the only difference is that it's 1 over r to the 6th because it's an induced dipole. Okay, so we're using transition, well, electric dipole transition moments. There used to be 2 erasers. So these electric dipole transition moments play the role of producing a dipole that can interact with the other dipole. And so, well, do we need this? Well, we don't really. If you had dipoles, then the interaction would be 1 over r cubed. But if one of the dipoles is 0, then the interaction is 1 over r to the 6th. And it's 1 over r to the 6th times the permanent dipole of 1 and this thing from perturbation theory, which is the induced dipole of the other. Suppose mu A equals 0 and mu B equals 0. Will the particles interact with each other? Will attract each other? And the answer is yes. And it's going to be an induced dipole interaction, which, now, since most people who write for general science have no clue about what quantum mechanics is, they will talk about all sorts of fanciful things. You get an instantaneous fluctuation on one particle, which creates an instantaneous fluctuation on the other particle, and bam, you've got stabilization. Well, yeah, maybe, but this is just simple perturbation theory. And so I don't really need to actually write out everything, because when you do that and you include the second order perturbation expression for particle A and particle B, you get a term that looks just like this. It has 1 over r to the 6th. But it now involves transition moments on particle A and particle B. Nothing new. You don't have to induce anything more. You don't get another factor of 1 over r cubed. You've already got the 1 over r to the 6th. So I'm going to skip a lot of steps because the notes are really clear and we don't have a whole lot of time. And so I'm just going to write down the result. And now the name of this term is called dispersion, or London, because a fellow by the name of London invented this. The energy level formula for this correction term is 1 over 4 pi squared epsilon 0 squared r to the 6th. And then this sum of alpha equals 1, beta equals 1 to infinity. In other words, not alpha equals 0, not beta equals 0. And then sorry about that. So we have a numerator, which is the squared transition moments between the 0 level of particle A and the alpha level, and the 0 level of B and the beta level. We have the energy of the ground state, and we have the energy of these excited states. All of this stuff you know. or at least you can parameterize it in terms of this strength of a transition. And there's an explicit formula that relates the dipole moment to the energy, to the intensity, depending on what kind of experiment you do. So I'm not going to take you through that, but you know you can measure the intensity, the molar absorptivity, or whatever you want that is related to this. And so these are experimentally observable. These are experimentally observable. And usually this infinite sum is dominated by the lowest allowed transition from the ground state. And that can be an electronic transition or a vibrational transition. So for a homonuclear molecule, there isn't going to be an allowed vibrational transition. So nitrogen and oxygen cannot talk to each other through vibrational transition dipoles, because the dipole moment is not dependent on internucleus, but they have electronic transitions. And so there's this electronic as opposed to vibrational polarizability of the two, and that's what gives rise to attraction between N2 and O2, or N2 and N2. So everything is knowable and predictable. And even though the perturbation sum is infinite, and even though we've made a gross approximation and say, well, we're just interested in this sort of an interaction, or this sort of an interaction. And we know that the true interaction will be less, because there will be an average over all of the random orientations, but there's going to be a lowest energy picture, and you can get that from statistical mechanics. And so you can do the configurational average over all possible orientations of all of the interacting particles, and you can calculate this. So that's beyond the level of this course, but the engine of the calculation is this formula. So molecules are polarizable. They react to an external electric field. And there are several ways you can define polarizability. One is to say, well, the polarizability, let's call it alpha, is equal to the second derivative of the energy with respect to the electric field. But the polarizability, you also get from perturbation theory. And so each of these terms, or the energies associated with the interaction of a dipole with an electric field, is the electric field times a dipole. And so we have electric field squared. We take the second derivative of that, and we've got back to this. So now here we come with intuition. If I asked you to tell me the van der Waals, or the dispersion interaction between helium and helium, and compare that to xenon with xenon, would you be able to tell me? So which one is stronger? Which pair of inert gases is stickier? Xenon, right. Why? Because the energy denominator for the first excited state is much lower for xenon than for helium. Okay, what about large molecule versus small molecule? Do I need to provide a hint? 3n minus 6. The more vibrational modes, the more transitions are available for polarization. And so again, now we're talking about molecules which can be floppy, and the floppier the molecule, that means they have low frequency vibrations. You can polarize the daylights out of them. And so large molecules are really sticky, stickier than inert gases, because you have this dispersion interaction that brings them together. And once they're together, then they can do magic. But the thing that drives the condensation or the formation of droplets or whatever is this dispersion interaction. And it's universal. Every pair of molecules or atoms is going to attract each other. And the strength is something that you can rate in terms of what you know about atomic and molecular properties. And isn't that neat? Because you're saying the viscosity or whatever it is, that the property of a gas, all of those things are related to the properties of the individual atoms or molecules embedded in perturbation theory. This is why I think perturbation theory is so wonderful, because it enables you to relate different things. And even if you're not going to evaluate the magnitudes of the terms, you can make comparisons which are always going to be right. And that's kind of wonderful. I mean, you don't have to use the equations, or you just know that these particles will attract each other, and the driving force is either a permanent or an induced dipole. And the induced dipole will be strong if you have a strong transition to a low-lying state, or a lot of strong transitions to a lot of low-lying states, as you have in big molecules. Okay, so I'm not positive what I'm going to talk about on Friday. It's probably going to be photochemistry, but I may panic and do something else. Okay, I'll see you Friday.